In this section of chapter 17, I'll discuss about common ion effect and also will give you an understanding of buffer action. That means how buffer solutions work to prevent change in pH of a solution when you add a little bit of acid or a base to the solution. Common ion effect. Now, let me give you a simple example. Say I put a weak acid in water. Weak acid could be any of the organic acids like formic acid, acetic acid, citric acid. So I'm just writing down as HA. And that would break down partially. That means out of maybe 100, one of them would break down, giving H plus and A minus. Now, if I add A minus through another compound could be sodium of that compound. Say if I add sodium NaA, NaA is going to break down into Na plus and A minus. So that means it's going to contribute A minus and is going to increase the concentration of A minus. And that's common ion effect. So sodium A, NaA, has A minus, HA also has A minus. So in other words, that's the common ion. Now, how does common ion effect work here? We are going to apply Le Chatelier's principle. First, without adding NaA, you would have H plus and A minus solely coming from weak acid HA. When you added NaA, that contributes A minus, so the A minus concentration is going to increase. So when this concentration is going to increase, equilibrium would be shifted to the left. In other words, A minus would be used up. When A minus is used up in forming HA, H plus is also going to be bonded. So in other words, H plus concentration is going to decrease. Decrease in H plus concentration means increase in pH. Let me explain that to you. pH is minus log of H plus, or if you know about logarithmic algebra, it's log of inverse of H plus. So we can better understand it. When H plus is decreasing, if H plus is decreasing, pH has to increase. So keep that in mind. In this slide, we have HNO2 that breaks down into H plus and NO2 minus. Again, if I'm adding sodium nitrite, NaNO2, all sodium salt would break down 100% into sodium plus and the other ion. As soon as I add sodium nitrite, NO2 minus or nitrite concentration is going to increase because that's the common ion. So as NO2 minus concentration is increased, equilibrium will be shifted from right to the left. In other words, as the reaction happens back in a backward manner from NO2 to HNO2, H plus would be used up. More of the H plus would be used up. So H plus concentration is going to decrease. And what that means is pH is going to increase. pH increase means solution is getting more basic. Another example, CH3NH2. This is a weak base. It's methylamine where nitrogen has a pair of electrons. Keep in mind, nitrogen would like to have, especially the neutral nitrogen compound, would like to have 3 bonds with a pair of electrons on nitrogen. So it's similar to ammonia. This gives you an idea that why amines act as a base. So this is ammonia. So in order to get amine, one of these hydrogens or 2 of these hydrogens can be replaced by methyl, ethyl, or another group. Anyway, this is the basic reaction you're looking at, the top reaction. With water, it gives CH3NH3 plus and OH minus. Because water breaks down as H plus and OH minus. H plus goes with NH2 and OH gets separated. And OH minus is responsible for the basic property for which CH3NH2 is known to be basic. If I use second compound, which is CH3NH3Cl, again the chlorides, most of these chlorides also break down, not all chlorides, but most of them. And in this particular case, this is going to happen. Cl minus is going to get separated from here. So this is the methyl ammonium ion, and that's the common ion. And whenever you increase the common ion, again, equilibrium would be shifted from right to the left. In this particular case, OH minus concentration would go down with time. Now, OH minus concentration going down means pH would go down. Now, there's several ways you can understand that. Now, pH plus POH is a fixed number, which is 14. When OH is going down, let me write down POH in a different way, log of inverse of OH minus, or log of minus log of OH minus, the same thing. So this is POH. POH is this, log of inverse of OH minus or minus log of OH minus is the same thing. Now when OH is going down, that means POH would be going up. When POH would be going up, since some of these two numbers would be 14 or fixed number, when one is going up, the other one has to go down. So that means pH will have to go down or pH decreases. The other way of looking at it be OH minus stands for basic property. When the basic property is going down with the downward trend of OH minus, acidic property has to go up, because H plus times OH minus is a fixed number, 10 to the negative 14. So if one goes down, the other one has to go up. Either way, you can think about this problem and it come up with the same answer. Sodium formate, again this is the weak acid, HA we are considering a sodium formate that splits into H plus and A minus, and only partially this kind of dissociation happens because it's a weak acid. If I'm adding sodium formate, sodium salt, as I mentioned, 100% sodium would come out of it. So you'd have formate ion, A minus. As soon as you add sodium formate, the formate ion concentration would increase in the solution. And so Le Chatelier's principle tells us that as A minus concentration or formate ion concentrations increase, equilibrium would be shifted from right to the left. That would consume additional amount of H plus. In other words, H plus concentration is going to decrease and pH is going to increase. Now I'm adding KBr to HBr. HBr would break down into H plus Br minus. Now this is a common error that when we ask that KBr when it's added is going to contribute Br minus, so there's a common ion. If you don't look at this problem carefully, you may think that equilibrium will be shifted from right to the left. But truly, that's not going to happen. Why? HBr is a strong acid. It doesn't like to hold on to its H plus. It would 100% break down into H plus and Br minus. So even when Br minus concentration is increased, equilibrium would not be shifted to the left, because HBr is so strong acid, it doesn't want to hold on to H plus. So equilibrium would not be shifted, so there'd be no effect of addition of Br minus in this case. So pH would remain unchanged. So H plus concentration would also be unchanged. Here we are going to discuss what buffer solution is and what is the composition of a buffer solution. Just to remind you that buffer solution is the solution that resists a change in pH upon addition of small amounts of acid or base. There are many examples of buffer. Our blood is a good example of buffer, and it maintains that pH even if you're drinking lemon juice or taking antacid tablet. Now, composition is made up of a weak acid and its conjugate base, or weak acid and salt of a weak acid. Now, if you look at the weak acid H2CO3, conjugate base of the weak acid is HCO3 minus. So basically I can have H2CO3 and HCO3 minus, and that would make a buffer solution. So I can write down here H2CO3 and HCO3 minus. But you know that HCO3 minus comes in a compound, so in a salt. So we often say that it's H2CO3 and a sodium compound. So it'd be sodium bicarbonate, because sodium bicarbonate, sodium would get separated, so you basically get HCO3 minus. So this would be a composition of a buffer solution. You have a weak acid and the salt of a weak acid. It can also be a weak base and its conjugate acid. It works the same manner. I'm going to explain soon how this buffer action happens, why this kind of solutions resist change in pH. Now, if you look at number 1, you are adding H plus from the top, and there is just water in here, so there's nothing else. So as you are adding H plus, obviously H plus concentration in water is going to increase. In other words, water is going to be more and more acidic. More acidic means pH is going to decrease. So pH in case 1 decreases because it's getting more and more acidic. More acidic means a smaller pH value. Remember, pH 7 is neutral and lower than 7 is acidic. So more acidic means smaller pH value. Of course, you can also think in terms of the definition log of inverse of H plus or minus log of H plus. That's how pH is defined. In the third case, we're adding OH minus to water. So as you're adding more and more OH in water, so OH concentration is going to increase in water. So it's getting more and more basic. What that means is pH has to increase. More basic means increased pH. Again, remember, pH equals to 7 is neutral, 8 is basic, 9 is even more basic. So in 1 and 3, pH changes as you are adding H plus or OH minus to a solution. Now let's focus on number 2. In this case, we are adding H plus, but there is something which is grabbing H plus. What is that something? Which is HCO3 minus. So I'm underlining that. This is HCO3 minus. As soon as it finds H plus, it's going to combine with that, and it changes to H2CO3. Since H2CO3 is a weak acid, it doesn't like to break down. Only very few of them would break down. So basically it would like to hold on to its H plus. So you are adding H plus, but that H plus is not increasing H plus concentration in your water solution, because that water solution has HCO3 minus to grab H plus. So even though you are adding H plus, but there is no change happening in H plus concentration, and hence no change in pH. On the other hand, if I add OH minus to the same solution, this time OH minus is going to react with H2CO3. H2CO3 reacts with OH minus. Let me show you. I think I didn't write down that reaction here. H2CO3, that's the other species in the solution. When you add OH minus, it gives you HCO3 minus plus H2O. So this HCO3 minus is, in other words, H2CO3 is converted into HCO3 minus, but OH minus would not be available in water to show increase in basic property. So this tells you that weak acid, H2CO3 is a weak acid, HCO3 minus is the conjugate base of the weak acid. Whenever you have a mixture of both, it's going to act as a buffer solution. And whenever you add H plus, HCO3 minus would be there to grab it. When you add OH minus, H2CO3 would be there to grab it. So overall, there'd be no change in concentration or no change in pH. This is a simple analogy that we are showing you. A number of candies are lying on the table and there is no one to grab those candies. This is the situation of adding H plus or OH minus in water and there is no one or nothing to grab those H plus or OH minus. So this is the case in case 1 and 3 where pH is going to change. Now here you see somebody came in and she's candy lover. So as soon as she comes in and sees all these candies lying on the table, see what is going to happen. Now this is comparable to H plus when you are adding or lying in the solution. If there are H2CO3 or HCO3 minus, HCO3 minus is going to grab H pluses. So the role of that HCO3 minus would be like this lady who would like to grab candies. Now all the candies are gone. Similarly, when H plus or OH minus is added, if there is some kind of species to grab them, then there'll be no H plus or OH minus lying in the solution to cause any change in pH. Now the question is, if you keep on adding candies, would this lady keep on eating them? No, our common sense would say that there's a limit. Beyond that, you're not going to consume any more candies. Just like think about Halloween candies. And that's the capacity. Same would be the case with buffer solution. If you keep on adding, like in this example, you're adding OH minus. H2CO3 is going to react with OH minus. Basically, it's going to grab OH minus and change it to HCO3 minus and H2O. The question is it going to grab OH minus forever? No. You reach a limit. What is that limit? All these H2CO3 that you see in the solution, they'll be all gone. They'll be all reacting with OH minus and there'll be no more absorption of OH minus. Then again, pH is going to change again. It becomes more and more basic. And that's called buffer capacity.